Good morning, good afternoon, and good evening to you in different parts of the world. Thanks for the invitation from Air Infiltration and Ventilation Center. My name is Jie, and I completed my PhD in UNSW last year in Professor St. Maurice team. I'm happy to share with you today about some recent developments of supercool materials and to depict a specific picture about the supercool roofs applied and tested in our previous cool roof project, which Ricardo just presented. By saying supercool materials, I'm referring to radiative cooling materials, which Matt just mentioned. It is also the topic of my PhD research in the last 4 years. Okay, this is an outline about what I'm going to present. We'll start with the introduction about the fundamentals of supercool materials, about what kind of properties or thermal mechanism can lead to the supercool performance of a material. We'll have a look at the material types, their performance and limitations, and also its huge impact on energy and also on the large-scale environment, as well as its commercialization. Then we'll highlight some recent developments to further increase the cooling performance of such a material. Finally, it's the summary and outlook. We'll start with the fundamentals. For a roof in summer, apart from the non-radiative heat exchange with the surroundings, you can see this gray part, it also absorbs heat from the following sources. First, solar radiation, and second, the long-wave radiation coming from the atmosphere. And heat dissipation is mainly through the thermal emission coming out from the material. And according to Kirchhoff's law of thermal radiation, in thermodynamic equilibrium, emissivity equals to the absorptance. And this is the fundamental knowledge. And conventional cool roof materials, they largely focus on minimizing the absorption of solar radiation. That is why we often have the light-colored roof, the white roof, or some colored roof with high reflectance in the near-infrared range. On this basis, if we have a look at the curves of the outgoing, I'll turn on the pointer, maybe. Yeah. If we have a look at the curves of the outgoing emission, here we have the black body radiation spectrum of material of 300 Kelvin, the temperature, and also the incoming radiation from the atmosphere. Here we have the colored curves showing the ambient radiation for 3 cities, Singapore, Sydney, and Alice Springs. If you have a look at this picture, we can notice a large difference in the 8 to 13 microns between the incoming and outgoing radiation. This means that in 8 to 13 microns, outgoing heat, this black line, it outweighs the incoming part. And the greater the emissivity or the absorptance, the greater the net heat dissipation. That is why 8 to 13 microns is also called the atmospheric window. We hope on the basis of heat rejection in solar range, we also have the high emissivity in atmospheric window, 8 to 13 microns, to maximize the heat dissipation. They work together to generate a supercool material. Therefore, for an ideal supercool material, it always contains 2 parts, a reflector to reject most of the solar radiation, and an emitter with high emissivity in 8 to 13 microns. Whether the ideal emitter should be selective, you can see here the red solid line. This is the curve, emissivity curve for a selective ideal radiative cooler, or it should be broadband. This is depending on the specific climate. Yeah. A radiative cooler reported in 2014 attracted great scientific attention. This is the very first one here. It is a one-dimension photonic crystal and its surface temperature reached sub-ambient, meaning even exposed to direct sun, the material is still cooler than the ambient air. In this case, the roof can cool both the substrate and also the surrounding air. Since then, photonic crystals of 1 dimension, 2 dimensions, and even multiple dimensions have been fabricated and tested, and subambient records has been frequently refreshed. But the manufacture of the photonic crystals, it requires precise beam evaporation or photolithography, which are often not cost-effective, therefore restricting the large-scale application of the photonic crystals as radiative coolers. Yeah. To facilitate the application of supercool materials in buildings or even at the city scale, radiative coolers in forms of film, paintings, or sprays have been reported. One of the ideas is to embed the reflecting or emitting particles into solvent or transparent polymer base to create the corresponding products. As you can see here, it is a summary of such materials in recent years. It has been proven that such materials can also reach the reflectance and emissivity comparable to the previous photonic crystals, and also in subambient temperature and cooling power. They have comparable cooling performance. Yeah, there are also some commercially available polymers can be intrinsically used as the emitter. People found that if you look at here, if a polymer contains some certain functional groups, it will have high emissivity in 8 to 13 microns. Some examples here, like the Tetler PVF from DuPont, it was firstly tested for cooling purpose in 1975 in Italy. Together with the reflective layer, it has subambient cooling performance. Even at that time, subambient cooling performance. Later, more films have been reported effective, such as you can see here, the TPX, the 3M ESR, etc. They can be applied in the forms of regional film or to be made into particles and become a new mixture together with some other ingredients. Yeah, in October 2020, we tested a group of polymers and either individually or combined with other layers. Matt just presented our results and I won't introduce in detail here. The result is that with peak solar radiation exceeding 1000 watts per square meter, we have the 4 groups of samples kept subambient temperature, surface temperature, which is up to 5 degrees cooler than the air even during peak hours. Yeah, here is a brief summary about the optical properties and cooling performance of some recently reported designs. You can see here we have emittance, reflectance, the subambient temperature, and net cooling power. But please note that the reported performance of coolers cannot be compared directly. Why? Because samples from different papers, they were tested under different climates and using non-identical experimental settings. Therefore, we just extracted values just for your reference. They can't be compared directly. In other words, we need to be objective about the cooling performance reported from various samples from numerous papers. And here is some evidence informing you that the performance of cool materials has certain limitations. For example, when the same material was tested in 3 different American cities under different sky conditions, precipitable water levels, as well as air temperature, we see different subambient temperatures and cooling power. And similarly, in one of our previous studies, we simulated 3 different coolers in 3 different cities, including Sydney, Alice Springs, and Singapore, for a typical summer month. We found that the 3 materials can almost all reach subambient in Desert City, which is the Alice Springs. Right here, they can all reach subambient temperature, but all have above ambient temperature in Singapore, whilst in Sydney, they have intermediate performance. Another example is that for the same material using identical experimental settings, the cooler reached up to 5 degrees subambient in California, you can see on the right side, but cannot be cooler than air in all testing conditions in Hong Kong, which is here. This is mainly believed to be caused by the high ambient radiation in cities with humid climate, and therefore we need to consider the specific climate, which can be the limitations to the performance of the materials. And one possible solution for this humid climate is this asymmetric transmission window. You can see it has different transmittance for the forward light and the backward light. If we allow the emission to go out, but block the certain part of the incoming radiation, long wave radiation, it can eliminate the side effect of the humid climate to a large extent. Yeah. Despite the heat in scientific research, very, very few supercool materials designs or products have been commercialized. This brand is called venticool. It was established in Ningbo, China. It is the first company commercializing radiative cooling materials worldwide. And it was based on the research outcome first published in Science in 2017. The research team then established the company based on the research outcome. You can see the products on their website include films, metal sheets, and paints, and etc. For example, this specific product called Radicool Reflective Film, it was claimed to have a cooling power of around 130 watts per square meter. Yeah, here we provide you with their website. You can go over and have a look after this webinar. Regarding the field of application of cool materials, apart from buildings, facade, and roof, we also have some certain fields that can have potential for the application. For example, the industrial plant, the outdoor goods, the solar photovoltaics, and also you can see here the electrical equipment, agricultural facilities, etc. Whenever or wherever we need cooling, these materials can have some role in cooling that facility. Yeah. So what is the impact of the application of such material? Let's have a look at the building scale or the energy scale. On the building level, we see the significant drop of roof surface temperature after applying cool roofs, as well as the decrease in cooling energy consumption, as you can see here. In our recent research, we compared energy saving potential of cool roofs in Australia cities during the year. We found that the radiative cooling roof can reduce more of the annual energy consumption in a cooling dominated climate. If we have insulation, the difference between different roofs that can be largely decreased. Yeah, this is pretty much our research outcome by using the energy simulation. If supercool roofs have been applied at a large scale, what will happen? In our research last year, 3 supercool materials, you can see A, B, C here, they have been applied to the entire city of Kolkata, an Indian city, using the weather research forecasting model. The simulated results show that the maximum reduction of peak ambient temperature can be up to 5.3 degrees. That is because of the application of supercool materials, and it actually reduces the maximum, the peak ambient temperature of the entire city. Yeah, here we come to the second part. Let's have a look at some recent developments to further increase the cooling performance of such materials. We first introduced the fluorescent material. when exposed to the direct sun, we know that fluorescent particles can convert part of the absorbed sunlight into fluorescent emission, and then increase the effective solar reflectance, and therefore enhancing the overall cooling power. It can be applied to common building materials, for example, the polymers, paints, and also the glass microspheres we talked about just now. And later, Samira will share details about fluorescent cooling material, and I'll stop at this point. Secondly, it is well known that reflective particles in coatings tend to aggregate. The aggregation of particles not only reduces light scattering efficiency due to the overlapping of the particles, but also adversely affect other physical properties of the material. In a very recent study, cool coatings formulated using polymer encapsulated particles, it can result in improvement of up to 10% of the total reflectance, and therefore it can improve the cooling efficiency accordingly. The very last approach to increase the solar reflectance, it was inspired by a very common experience. I believe we all have the experience seeing water when water freezes to ice. It usually changed from transparent to white, becoming much more reflective, right? This is because the air particles previously dissolved in water, they become excluded from ice during the freezing. That comes to an idea. What about adding some air void to some transparent emissive polymer we mentioned previously? Can they be reflective using this approach? The answer is yes. Adding air voids into a transparent polymer, in other words, making it porous, allowing allowing the originally emissive layer to be both emissive and reflective. Yeah, and also this technique is compatible with a wide range of polymers, allowing optically suitable polymers to be easily transformed to excellent radiative cooling coatings. And at the same time, if we have large amount of pores, it can improve the insulating ability of the material as well. Finally, to summarize, the supercool materials. Specifically, we talked about radiative cooling materials. It has undergone nearly 10 years of rapid development and improvement. Various material types, fabrication approaches, optimizing pathways, and possible applications have been explored, and it is making strides towards the mature commercialization. But on the other hand, it still has certain limits in overcooling, for example, overcooling at night, mechanical performance, degradation, broader application, and also the possibility to integrate other necessary functions. For example, it has to be have the fire resistance and insulating property as well. Yeah, that's pretty much about my presentation today. And thanks for your attention, and we may discuss in the session later if you have any question.